Welcome everybody. So we will continue with Shamik's lecture. So Shamik has uh, one and two more next week. So three more lectures, right? Or
Three,
what is the
yeah, three more actually. So this is
three more?
the fifth lecture.
Yes. You've got three
Yeah,
more lectures. Yeah. So
yeah, I think that
seven.
will be fine because I think I'm doing quite well with the time actually.
Very good. Yeah. Okay.
Yeah,
Okay. Yeah. So you can start the
yeah,
recording.
yeah. So last time actually we talked about the conformal soft theorems. Okay, so this was like, well, so you can have a, but then we had the leading soft graviton, which say the leading positive helicity soft graviton actually. So leading positive helicity outgoing. Yeah, so that was denoted by S plus 1 z bar, and then this object, this leading soft operator, so that was basically in Fock space. So this was defined in this way. So this is the outgoing. And then we saw that this can also be defined as this way, okay? So where this G plus delta ZZ bar, so that is the Mellin transform of the annihilation operator. Similarly, the subleading soft graviton operator, well, I mean, we did not show it explicitly, but one can just repeat the same procedure. And so that is like S plus 0 ZZ bar, and that is defined as sorry. And in the conformal and for this operator, so delta going to 0, delta times G plus delta ZZ bar. Okay, so so you can see that you can also write it in this way, that as delta goes to 0 or delta goes to 1, so this goes like this. So this should be thought of as an operator relation. So G plus delta has different kinds of poles. You can think of in that sense, delta going to 0. Well, I mean, there may be some minus half and all these things that of course depends on. Okay, and so on. So, and the important point is that we saw that this S plus 1 ZZ bar, so that is actually basically it's a pair of hard hens which are like P0Z, P minus 1Z. Okay, so these are the super translation currents. Okay, so we decompose this as in this one. Okay, so now the question is that, of course, what happens to this subleading object? Okay, so this subleading soft graviton theorem. So okay, now let's talk about the subleading soft graviton theorem, and this is due to Cashazo and Strominger. Okay, and last time actually we wrote this down. So this is given by, so if I insert this inside a correlation function, so this object is essentially the right hand side of this equation will be given by the Kaczazos from Hinger subleading soft graviton theorem, and it has the form. So let me write it. So this is the form in after the Mifflin transformation. Okay, because that is the thing that we are interested in. So of course we get this factorized form. Okay. Okay, now we want to see that what kind of word identity is this. So the leading soft graviton, or the leading soft graviton theorem. So, or this is due to Weinberg, is equivalent to the word identity for the super translation. So now the question is that what about the subleading soft graviton theorem, or the Kaczazov-Strominger soft graviton theorem? So this is equivalent to what? Okay. So this was so now actually from now on, basically whatever I'll do, this is essentially in our recent paper. So okay, or basically you can say what kind of asymptotic symmetry is that. So this is of course basically the first part. So this will be used when you compute the scattering amplitude. So we have to first do this thing. Okay. So what we did in the case of the leading soft graviton was basically we did a z bar expansion of the right hand side. Okay, of the essentially the soft factor. So in this case also, what we so you can see that in this case it so this has a z bar dependence, which is, so it is like z bar square and constant in z bar. So those three terms are there. So what you can say is that we should first, so what we will do is that we will first expand this in power the right hand side of this, or basically this soft factor in powers of the z bar. Okay. So the first thing is that, so expand basically, so expand the right hand side or basically, or okay, or expand the subleading soft factor in powers of z bar. Okay. So if we do that, we'll get the following thing. Okay, I think I have some notation. So last time I said this is plus 1, 0. Okay, this is fine. This is plus 0. Okay. Okay, in powers of z bar. So let me actually write it in the next page. Okay, so this is a z bar to the power 0 term, and then so this del bar k is essentially a shorthand for this del z bar of k. Okay, now in this form, so now it is recognizable. Okay, so we got, so this is the basically the order z bar to the power 0 term. Okay, and this is the order z bar term, and this is order z bar square term. Okay, so what we can do now is that we can write down an similar expansion for the subleadings of graviton in powers of the z bar. So if we do that, then what we'll get is that essentially you have this object, which is j uh, minus j, sorry, this is the j0z. Well, the notation will be clear actually that I'm writing this. So let me expand this in this way. Okay. So what I have done is that I have defined 3 currents, j plus 1z, j0z, and j minus z, j minus 1z. Okay, and their correlation functions are given by this. So you can easily read it out from here. So it is just given by this. So this minus sign is gone, already absorbed this. So this becomes just okay. And so on actually. Okay, so let me just write this thing. So this is the first one, first current, then this is just and the okay. So we got this. So now, so now, if you are just like in the case of the linking of graviton, so we have this, instead of two, we have three now, three word identities, and so each of the word identities. So you can see from here, from these three word identities, is for due to this j plus one, j0z, and this j minus one z. So you can see that the global symmetry generated by j plus 1z is essentially, we just have to look at the residue of the pole at z equal to zk, okay, and that immediately gives me that you can write it as delta plus 1 phi epsilon So this is the global, okay, so let me emphasize this thing, the global symmetry. Okay, now, so what is this object? So this is essentially, you can write the action of L1 bar on phi epsilon HH bar, right? So this, so this now then delta naught, which is generated by J naught Z. So so that object is actually H bar. So that is L0 bar. And similarly, the delta minus 1 is essentially the translation in the anti-holomorphic coordinate. And that is L bar minus 1 common phi epsilon. This is object. Okay, so you can see that why. So now you can see that this well, by the standard way, like, so we have all these three holomorphic currents. So this is plus minus 1 and J0Z. So they, of course, since they are holomorphic, they generate an infinite dimensional symmetry algebra whose global part is the same as the anti-holomorphic global conformal transformations. Whose generators are, of course, we know L bar plus minus 1 and L0 bar. Okay, so that's why. So this, so basically, so that's why we'll call basically the, so this is the reason why the basically the subleading soft graviton theorem well, subleading positive helicity. Okay, I'm only talking about positive helicity objects. The negative helicity, just do a conjugation. So subleading positive helicity soft graviton theorem is essentially the same as the word identity for SL2C. I call it bar because it is the anti-holomorphic. So it is the SL2C which is acting on the anti-holomorphic coordinates. Okay, so this sorry, L0 bar and L bar plus minus 1. So this is the same as the word identity for the SL2C bar coveredin algebra. Okay, so this is essentially the thing that we need. And now, of course, we can define in the standard way. So what we can do is that we can define the modes. The modes JAN, where this A is 0 or plus minus 0 and plus minus 1, and this N is an integer. Okay, so we can define the modes JAN, which generate the local so this is important actually. Okay. There. So this is a local symmetry algebra. SL2C bar transformations. Okay, and how do they act? So you can write it as say delta plus 1 n. So this is the action of j plus 1 n on the field. This is essentially you multiply as z to the power n, and then you have z bar square d bar plus 2h bar z bar. Okay, similarly delta 0 n. Okay, or you can also write them in terms of commutator like this. This will be like z to the power n. And so on. Okay. So this is essentially the transformation. So you can see that now this has become local. So because well, I mean, this n is an integer, so it can be both positive and negative integers. Okay, and the point is that this will be, so this n can, yeah. So you also have singular transformations. Okay. So this is essentially the algebra, and then you can of course compute the commutators of the generators JAN, and that will be given by the where this you have like this A, B, and this N. They are integers. Okay, and A, B are 0, plus minus 1. So this is the SL2 current. So SL2 current algebra with level k equal to 0. Okay, now this actually is true. So this particular statement, so I should mention that true at least at tree level. Okay, because once you consider loops, so with loops, this soft graviton, this subleading soft graviton theorem itself will change. And well, I mean that of course we have not actually stuck it that thing, but things can change, or they will just be same. But we have not actually worked on. We don't know actually what will be the answer. So it is important that this is at tree level. Okay.
I didn't quite follow that last comment, Shamik. When did we introduce a loop counting parameter anywhere in this discussion?
Well, the loop counting parameter, of course, was well, I mean, you had a kappa, which I have said equal to 2. So that actually is one such thing. But the point is that once you have the loop, so you can get some extra terms which come because of the infrared divergence.
Oh,
Okay.
for the because of the infrared divergences.
Yeah.
But okay, okay. I see.
Yeah, so you get certain extra terms from there, and it turns out that actually this was also started by Strauchinger et al. So it turns out that the one loop is actually exact. I mean, so these terms are actually one loop exact, but they are not necessarily zero. Okay. So you can have some additional terms.
Okay.
Yeah. And the other point, yeah. So that's a yes. So I have actually said, just like in the last lecture in the third lecture actually. So I have said kappa equal to 2. Okay. So kappa is square root of g Newton. Because otherwise, I mean, you will have factors of kappa. I mean, that you can always introduce without any. Uh, Yeah. So is there any other question at this point?
Hi, I had a question.
Yeah, please.
Yeah, so the transformation group that you obtain from this subleading soft graviton theorem, is it got anything to do with the super rotation group, which we
No,
get in
no. So let me actually clarify that. So
since
super
at the
rotation.
leading order we had got the super translation. So
Yeah, no. So
yeah.
that is the thing. So the super rotation is the same as a Virasoro from the field theory point of view. Okay. So this is not that. So what we have obtained. Okay. So this if can get if you do a shadow transformation. Transformation, I think, yeah. Okay.
Okay.
Yeah. So actually, let me just see. So I'll not go into this because for the image amplitude, we don't need this. We just need this SL2C bar and the super translations. So that's all we need actually. So that's why I'll not be talking about that. But this is a very important fact, and this actually, yeah. So, but well, it and that's why like it's actually it's called a conformal field theory. But the point is that in order to get it, you have to do a shadow transformation of these subleadings of graviton. Okay.
Okay.
Now,
Thank you.
actually, so let me just see if I can say more about. Well, I mean, if I remember this. Yeah. So you can actually, so you can do something more. I think. Let's see. So this S plus 0 ZZ bar. So this is a, of course, this is a conformal primary. Okay. So with scaling dimension. So this is delta plus, just let yeah, delta 0, sigma 1 minus 1. Okay, because h is delta plus sigma by 2 and h bar is delta minus sigma by 2. Okay, and s plus 0 zz bar that we obtained by setting delta equal to 0 and sigma of course here is plus 2, and that immediately gives you h bar equal to 1 minus 1. Okay, so now if you do a shadow transformation, of this operator, you get another another primary with dimension, since it's shadow, so the dimension will be 1 minus h and 1 minus h bar. So we started with 1 minus 1, so that gives me 0, 2. Okay. Now this is the dimension of the anti-holomorphic stress tensor T bar, right? So T bar, like this. Okay, and this one generates the SL2C bar current algebra. And this gives you the Virasoro. Okay.
Okay, fine. Okay.
Yeah. So that is the thing actually. Yeah. So is there any other question? Okay. So if there are no other questions, so let me just go ahead with this. So what is the, so now the question is that what is the complete, well, symmetry? Well, complete in the sense, I mean, before, I mean, if you don't do the, or complete symmetry, or okay, I should not call it a complete symmetry, but well, so basically, question is, what do we get from leading and subleading graviton theorem? Okay, so without shadow, I just want to mention, because with shadow you can also get this Virasoro, but we'll not be talking about that. So this actually, so this you can show if you take the shadow transformation of this identity, this one. Okay, here then this actually just gives you the standard identity, like say the one which you get in two-dimensional theory. Like, okay, in this case, of course, it will be, okay, so suppose just write it as T, and you can conjugate this like T of Z, and then we have some bunch of primaries. So this will be like some K. So you will get exactly this form. Okay. If you do a shadow transformation of this of the subleading subgraviton. Okay, and the references are there, so you can. I have already given the references, so you can look at that. But you get this form, so that's why we say that, I mean, if this TZ, so this generates the Virasoro. Okay. Okay, so now, okay, so what we got, so the leading soft graviton, we got two currents, the two super translation currents, and with the subleading soft graviton, we got three. So these are the super translations, and then we got these currents. So these are the SL2C bar currents. Okay. Now and then we of course have these modes PMN, okay, where say n equal to 0, -1, and n is an integer, okay. And then we also define these modes JAN, where a is 0 plus minus 1 and n is also an integer, okay. So we saw that this commutator is 0 because the super translations, the super translations, they form an abelian algebra, okay. We also looked at the commutators of these currents, the SL2C bar currents. Okay, actually, okay, so let me actually use a slightly different notation here. So let me not call it, so let me call it alpha. Okay. And okay, and so this was just a minus b, j plus b plus a. Okay, so here the identification was that the zero mode algebra, that is JA0. Okay, so this should be identified as like J plus 1 0. So so J plus 1 0 is L bar plus 1. Similarly, J0 0 is L bar 0, and J minus 1 0, that is L bar minus 1. So these are nice. So they close among themselves, which is expected. Now the good thing, or the somewhat surprising maybe, is that this algebra, they all also close. So this JP, this also has something like this. So they also close. And how does that algebra look like? So let me write it down. So the super translation and the SL2C bar current algebra form a closed algebra. Okay, and what is that algebra? So that algebra has this form. So all of these actually will be used later on. Oh, sorry, this is N. And the other super translations, their commutator is like this. Okay, so this is essentially the algebra. So this, you have the 6 computators, and then you have this object. For the sake of completeness, let me just write this down. Okay, so this is the algebra, and well, what al well, so this is essentially, you can think of this as a subalgebra of the much bigger algebra, which also, so this is basically, essentially, you can think of this as the subalgebra of the algebra, which also has Virasoro and SL2C current algebra. So this basically comes from the negative helicity subgravitons, subleading subgraviton. I mean, it is just conjugation. Okay. Just like if you take the Schachter transformation of the plus helicity subleading subgraviton, what you get is T bar. But then if you take the Schachter transformation of the negative helicity subgraviton, then what you get is T. Okay, so similarly, the same thing will happen here. So it's a much, so if you want to talk about the symmetries, the tree level symmetries in GRC. So that is this big algebra which has all these parts. But the thing is that this is a small part, which is a subalgebra of that. Okay. And the point is that it turns out that quite, well, I mean, it's not surprising, but the thing is that, well, I mean, I'll show that, I mean, why it's surprising, but if you think about it, you will see that, well, I mean, this is quite clear that it has to be the case, that basically the image V amplitudes, the graviton image V graviton scattering amplitudes, so the basically, so tree level, okay, tree level actually, and that we will see that all these things mix together in a nice way. So the tree level MHB graviton scattering amplitudes are completely determined by this symmetry algebra. By this closed subalgebra. Okay, which has these currents like P0Z, P minus 1Z, and GAZ. Okay, where A is 0 plus minus 1. Okay, so this is we'll see actually. Okay, so in the next lecture, I'm planning to talk about the OPE, that how does one do the OPE on the sphere. Like this will be, that is another factorization. Okay, and then after that, we will directly go to the imaging case. Well, so I have actually, well, so I have skipped one part, which I think I will not, well, I mean, I'll need that at every point, but I will not talk about that. Is basically the descendants of this local algebras. Like okay, so we also have the, so basically, so we have the phi, the primary field, say phi h bar, z bar. But then we also have the descendants of them. where for n is less than 0. Okay. Now, and also we have the super translation descendants like p n comma, or okay, let me then define notation. This is, sorry, this is JA minus n with n greater than 0, and this is like p minus n alpha phi h a bar z z bar for n greater than 0. Okay. And the point is that what we'll need are these correlation functions of the descendants. Some say. So those are of course found out in the standard way, just the way we do it in the conformal field in 2D CFT. So I'll not go through that. I'll just write down these expressions, and the same here. So these two things, they follow, of course, from word identity. Okay, I'll write down an OP expansion for these things. Okay, so because those OP expansions are the ones which we require. Okay, and that is very important actually. Okay, so I think I will stop here. Then next time actually I will be talking about the OPs, and then after that we can go into the calculation of this scattering amplitudes. Yeah, I think I'll stop here. So if you have any question, you should now ask me.
May I ask a question?
Yeah, sure, please.
Yeah. So, you know, as you have formulated it, this was like, I don't know how to show that equation, but in the equation, this was poles in delta. The delta minus one pole was Weinberg's leadings of theorem.
Yes,
and the next two were Kakazo-Strominger one.
Right.
But there will be other poles as well, right?
Yeah.
Beyond subleading,
right.
how will they be important in the story?
Yeah, good. So that I well, because I did not talk about that because I did not but let me, since you have asked it. So there are three soft factorization theorems. Basically, three soft graviton theorems. Okay, one is like delta equal to +1. So that is the leading or the Weinberg. And delta equal to 0. And delta equal to -1. So both of them basically are due to Kakazo-Strominger. Okay, now this delta equal to -1. So this is the subleading soft graviton theorem. Soft graviton theory. Okay, so basically, if you do any energy expansion, then it will be like this. So you have 1 over omega Sn plus order omega to the power 0 Sn plus omega, or sorry. Okay, I'm being very extremely schematic, so okay, so this is these are the first three factorization. Now the point is that the subleading you can talk about the subleading symmetry. Okay, just the same way that we talked about this. Now the interesting point is that this symmetry algebra does not close in that sense. So it's not a standard Lie algebra in that sense. So, but still you can actually work with this. Okay, and what we have seen is that, okay, so in the case of the image amplitudes, okay, so all the informations, like all the quote unquote relevant informations are contained in leading and subleading subgraviton theorem. Because the point is that the leading and subleading subgraviton theorem, so they completely fix this MHV amplitudes. So in a sense, the subleading should just come from that, and that is what we see at the algebraic. Now, the point is that you can ask what happens beyond this. Well, that is an interesting thing. So this algebra is known actually. So this algebra, well, I'm calling this algebra, but this is not a standard algebra in the sense that this will not close. Okay, but still you can work with that at the level to the extent we have seen that this does not play any important role. But the point is that there is another thing, which is that where this plays some role, and that is so that can be done in other ways also. But the point is that, okay, so that is essentially where the OP thing comes. So for example, okay, so I will discuss it next week, but let me just, so if I take, for example, the OPE of two gravitons like this, this is just okay. So
Shamik, can I just halt you a little bit? I have to go back to the interviews. So what
sure.
Stop recording, but you guys can continue discussing. I don't need to be.
Sure. It's fine.
I will stop the recording and then you guys continue discussing.
Sure.